This is your presenter Asloob Mudassar, and I am presenting slide number 131 of the course on laser physics. Question is, it is said that the laser spikes could also be obtained using gain switching process. What is the gain switching process and how it differs from the Q switching process? The answer is, gain switching is a process in which the gain of a laser medium is raised to a very high value, 5 to 10 times the threshold gain, in a short duration, a few hundreds of a nanosecond down to a few tens of a nanosecond, to generate short high peak power laser pulses. In a Q switching process, the cavity losses are switched to a low values in a short span of time, whereas in gain switching process, the cavity gain is switched to a very high value in a short span of time. A short but an intense pump pulse in square or bell shape is used to obtain fast population inversion to a level well above the threshold inversion. The inversion should build so quickly to the desired level before the cavity photons reach to a very high value and deplete the inversion. The cavity photons then appear as an intense laser pulse. If the pump rate Rp as a function of time has a square pulse of duration delta t, then the first photon spike should occur just before the interval delta t lapses. The occurrence of the spike brings the inversion below the threshold inversion, and no second photon spike will be possible until a second pump pulse raises the inversion back to the desired level. So here it is stated that one thing is that our pumping pulse should be very short, which is the requirement of the gain switching process. And if the Rp, that is if the pump rate Rp as a function of time has a square pulse duration delta t, then the first photon spike should occur just before the interval delta t lapses. So you see that it means that before the completion of the pump pulse, the photon pulse must have started. Then the photon spike should occur. It means that the photon spike should complete before the interval delta t lapses. The occurrence of the spike brings the inversion below the threshold value, because since the photon spike is very intense, and that makes the inversion to go below the value of the threshold inversion, and when the inversion is below the threshold value, no second peak is possible unless no second photon spike will be possible until a second pump pulse raises the inversion back to the desired level. So you see that when we talk about the critical inversion, that is the necessary condition for the lasing action to take place and for the photon pulse to be generated. So if our population inversion is below the level of the threshold value, then of course any lasing process cannot occur, and no lasing process will continue, and no lasers and no photon spikes will then occur. So the main condition is that our population inversion should at least be well above the value of the critical inversion. We shall be explaining these things in much greater detail in the next page. The process of gain switching requires the RP, that is the pump rate value, to be much greater than the value of the pump rate which is required in the CW laser operation. So you see that here we are comparing the pump rate for the gain switching process, which must be much greater than the pump rate required in a continuous laser wave operation. With the pump rate RP ranging from 5 to 10 times the RCP value, which is the critical or the threshold pump value, the photon pulse reaches to its peak value in a time 10 to 20 times the photon decay time tau c. So here you see that for the gain switching process, over RP, that is the pump rate, should be at least 5 to 10 times greater than the pump rate required to generate the RCP, that is the critical or the threshold pump value. So here we raise the inversion to be much greater than at least 5 to 10 times the value that is required for the lasing process, that is the required value of the RCP or the critical or the threshold pump value. So let me read again. With RB ranging from 5 to 10 times the RCP, that is the critical or the threshold pump value, the photon pulse reaches to its peak value in a time 10 to 20 times the photon decay time tau c. So you see that here we keep our photon decay time tau c much smaller, so that our photon pulse should be completed in a time 10 to 20 times the photon decay time tau c. If RP, that is the pump rate as a function of time, has a bell shape with such a full width half maximum that the photon pulse occurs at a time corresponding to the trailing edge of the pump pulse, then after the first photon spike has occurred, the remaining inversion would still be greater than the threshold inversion, leading to a second photon pulse, though with lower peak power. The second pulse would then correspond to the tail of the pump pulse. So the first photon pulse will be occurring at the trailing edge of the pump pulse, and the second pump pulse, if it occurs, that is if we survive with inversion just above the critical value of inversion, then of course the second photon pulse would then be able to occur, but of course with a lower peak power. The second pulse would then correspond to the tail of the pump pulse. The increase in peak pump pulse by shortening the increase in the peak pump pulse by shortening the pump pulse width would result in a more intense and narrower laser spikes. So if the pulse width of our pump is narrow and if it is intense, then of course correspondingly we can obtain a photon pulse more intense and narrower laser spikes, or the photon pulse can be obtained. Now you see that if you want to obtain a single pulse only, in the foregoing paragraph I have mentioned over here, for example, how you can obtain two pulses, one corresponding to the trailing edge of the full width half maximum of the pump rate. So if you have the pump pulse, then the trailing edge corresponding to the full width half maximum you can obtain. For example, if you obtain the first photon pulse at the trailing edge, then of course the second photon pulse can be obtained at the tail of the pump pulse, provided we have sufficient population inversion which is above the critical inversion that is required for the lasing action to take place. So here we have mentioned that how you can obtain the two photon pulses. Of course, one photon pulse will be greater in magnitude, that's having a very higher peak because of the large population inversion available, and this would correspond to, for example, the trailing edge of the pump pulse. Then most of the population inversion has decayed, contributing to the peak power in the photon pulse. So if the remaining inversion remains still above the critical value of the inversion, then of course the second photon pulse can also be obtained, but of course that would correspond to the region with which has a corresponding to the region with the tail of the pump pulse. And then of course the value of the pump pulse would be relatively smaller. So the increase in the peak pump pulse can be obtained by shortening the pump pulse width, and that would result in more intense and narrower laser spike. Now suppose that if you want to obtain a single spike from the single spike, a very intense spike and a very narrow spike, what would you do? Let's see that if this paragraph explains the answer or not. To avoid the decay of inversion through allowed spontaneous emission. So you see that here we are restricting that we do not want over inversion to decay through the spontaneous emission process. And what is the requirement then? The cavity photon decay tau c must be well lower than the lifetime tau of the upper laser level. So one condition that we are imposing is that the photon decay time tau c, that is any photon which is present in the laser cavity, and tau c is the time of the decay of such photons, that tau c must be much lower than the lifetime of the upper laser level, which is tau. So tau c must be much lower than tau. So this is the condition that we are imposing in addition to that. So this would require short gain switched pump pulse. So what we want? We want that our gain switched pump pulse should be very short. How much short? Shorter than the lifetime of the upper laser level. That is before the initiation of the spontaneous emission, our short gain switched pump pulse should have completed. So this would require our short gain switched pump pulse much shorter than the spontaneous emission lifetime. That is no spontaneous emission during the gain switched pump pulse. So read this statement. No spontaneous emission during the gain switched pump pulse. That is when we launch the gain switched pump pulse, no spontaneous emission should occur during that time. And when the pump pulse is completed, then of course after that one, the spontaneous emission could start or could take place. So it means that our gain switched pump pulse should be completed in a time span which should be smaller than the spontaneous lifetime. That is the upper state lifetime of the upper level laser, that is tau. So the width of so the time taken by our switched pump pulse to be completed should be shorter than the upper state lifetime tau of the laser. So this is the requirement if we want to produce a very intense photon spike. And we want that the spontaneous emission could not be started. And even if there are some photons in the cavity by any means, then those photons should have decayed by the time tau c. And here we are also imposing that the time of decay of the cavity photon tau c is also smaller than the lifetime of the upper state laser. That is the upper state level. So tau is the lifetime of the upper state level, and tau c should be smaller than the upper state lifetime of the laser. And the second is that the Q switched pump pulse should have completed in a time span which is shorter than the tau, that is the shorter than the lifetime of the upper laser level. So this thing will ensure the emission of a single very intense and narrow pulse to be generated through the laser beam, to be generated in the laser beam. And you know that when over laser in an ordinary laser system, when we talk about the population inversion to be greater than the critical inversion, then of course the spontaneous the stimulated emission process starts. And during the pumping process in an ordinary laser, what happens is that the spontaneous emission can start immediately, provided our pumping process is longer than the spontaneous lifetime, which is usually the case when we talk about, for example, continuous wave laser, where the pumping process is a continuous process, and during that process the spontaneous emission can of course occur even before the critical inversion is reached. And you know that after the critical inversion, the stimulated emission takes place, and of course, an intense lasing process starts, and an intense lasing laser beam is obtained. But you see that in the gain switched pump pulse, our requirement is that our gain switched pump pulse should be completed in a time span much less than the lifetime of the upper laser level, that is much less than, that is the time span in which the Q switched pump pulse is completed should be smaller than tau. And the second condition, that is no spontaneous emission during the gain switched pump pulse. So this is our requirement if we want to produce an intense and a single photon pulse beam to be generated in the lasing process through the Q switched pumping technique. And the second condition is that our lifetime of the cavity photon lifetime tau c should be also less than the lifetime of the upper laser level, because if any photons are available in the cavity, they must have decayed in a time span much smaller than the lifetime of the upper laser level. So these two conditions must be met if we want to generate a very narrow, high power impulse response or high power impulse from the laser. And here you see that in this paragraph, that is in the second last paragraph, we have discussed the two ways by which we can generate the two pulses can be generated. Because here we are assuming that our pump rate has a pulse which is larger than the lifetime of the upper state level of the laser. So here in principle, two photon pulses can be generated. One could correspond to the trailing edge of the full width half maximum of the pump pulse. And if it occurs at the trailing edge, that is the first photon pulse occurs at the trailing edge, then of course the second photon pulse will correspond to the tail of the pump pulse. So here we have defined that over if when we are talking about the pulse rate in the gain switching process, that must be much higher than the pump rate which is normally required for a continuous wave laser operation. Because in the gain switched process, over the pump rate which is required should be at least 5 to 10 times greater than the pump rate which is required in the CW laser operation. And the second is that the population inversion that we want to be achieved should be at least 5 to 10 times greater than the critical or the threshold pump value. And of course the inversion should also be much higher. So you see that with these one we can explain we have explained that how the gain switching process can ensure the emission of a very high intense of a very narrow and intense beam comparable with the beam obtained through the Q switching process. So this is the end of slide number 131.